Imagine building with Legos, but on a small nanoscale level. That's how metal organic frameworks, or MOFs, come together. In the realm of MOFs, the Lego blocks represent the metal ions and the organic linkers that come together to form complex, three-dimensional, porous structures that have unique properties. Over the years, scientists have studied these optical properties by shining light on them. UV-vis spectroscopy is used to study the absorption of light, and fluorescence spectroscopy is used to study the emission of light. These two techniques are well established and relatively easy to use. But here's the tricky part. These two techniques are only directly applicable to small molecules that can absorb and emit light. MOFs, on the other hand, are large structures, and when the particle size increases, scattering becomes significant. Scattering is simply a disturbance in the sample solution, which makes it difficult to obtain clear optical spectra. So scattering complicates MOF spectral acquisition, which creates a significant research gap. Bridging this gap is important because these materials and techniques are widely used in research and education. Our group has dedicated significant research efforts over the past few years to understand and enhance the current spectroscopic techniques. In the presented study, we are using MOF NU1000 as a model MOF system and two innovative spectroscopic techniques that were introduced by our group: linear polarized resonance synchronous spectroscopy and integrated sphere-assisted resonance synchronous spectroscopy. Using these two techniques, we are able to look at scattering in such a way that we can get an accurate understanding of the contributions of absorption, emission, and scattering to MOF spectra. So, by looking at the strengths and limitations of existing spectroscopic techniques, our group is paving way for new, exciting opportunities in the field of material characterization.